This is a special case of the general factorial design. A general factorial design is a design where possible combinations of the factors are represented. These designs all have k variables, each at 2 levels. These levels are called low and high. We will assume that the factors are fixed in these situations. Here is a checklist on how to analyze a factorial design. This is just a guide. We will do the following. 1. Estimate our effects. 2. Formulate a model. 3. Reduce our model so that only needed terms are left. 4. Assess model fit. 5. Interpret results based on our goal. So now we need to understand, why are low-level designs so important? The following are a few of the reasons why this type of design is very popular. The fact that they require a small number of runs is beneficial since one can get all of the required information with a small expenditure of resources. Another reason is that the analysis of these designs is quite simple and straightforward. Typically, good experimentation is sequential in nature, which means that you usually will not reach your goal with one experiment. These types of designs allow you to determine the most promising direction to continue experimenting in. Let's motivate this material with an example. This is a chemical example, where factor A is reactant concentration, and factor B is the amount of catalyst. The response here is the percentage of recovery. Notice that we have small n equal to 3 replicates of each of 4 treatment combinations, which leads to large n equal to 12 total runs. The simplest type of 2 to the k design is one with 2 factors, which is a 2 to the 2 design. Each factor has k equal to 2 levels, and the setup is one where each treatment combination is represented by a corner of a square. Notice that each treatment combination has a combination of pluses and minuses. The pluses indicate a high level and minuses indicate a low level. In the previous experiment, the treatment combinations are presented in a special order. A gentleman by the name of Frank Yates came up with an order, which we refer to as Yates order or standard order, to which we can write out all these designs. The order is found by utilizing letters to represent which factors have a plus sign for that run. Then the letters are put in alphabetical order. Since Yates realized that one treatment combination does not have any plus signs, he labeled that run as a 1 in parentheses. Each of the variables on the previous slide was coded as plus or minus. This is actually short for +1 and -1. All of these variable levels are coded. If we assume that the variables in their natural units are considered causes, then the formula on the slide is used to code the variables to the -1 and +1 levels. The question that you should be asking yourself is, what is the benefit of having the levels coded to minus and +1? The coding given on the previous slide causes the design to become orthogonal. An orthogonal design is one in which all of the inner products of any 2 columns is 0. The benefit of this is that we are mathematically forcing the covariances between the factor effect estimates to be 0. This does not mean that the factor effect estimates are independent. In the purest form, recall that independence implies 0 covariance, but the reverse does not apply. Another benefit to the +1, -1 coding is that it causes the designs to yield minimum variance of the estimates on a per observation basis. It also causes the variances of the estimates to be equal. Later on we will talk about something called a half normal plot, in which this equal variance is critical. Also, the products of columns among these factors are identical to the corresponding interaction columns for factors. No other coding does this. Now let's talk about analysis. The basic analysis for these designs is quite straightforward. We will first assess the main effects for each factor. This is the difference in the average response at the high and low levels. The main effect of an effector is just a bar at the high level of a minus a bar at the low level of a. One thing to be aware of here is that we have not taken into consideration the levels of any other factor. This means that we are averaging over the levels of all of the other factors. We assume that the differences are the same at all levels of each of the other factors. Here are the results for the chemical experiment. The main effect for is 8.34, and 4b is 5.0. What does this tell us about each factor? As it relates to the overall average for factor, tells us that as we change levels of factor, the average response increases by 8.34. For factor B, the average response decreases by 5.0. This plot is called a main effects plot. It is a way for us to visualize what the main effects are. You can see from the plot for factor As we change the level from low to high, we see that the average response increases, and vice versa for factor B. You can get an idea of how important a factor is by assessing the slope of these lines. If the line is horizontal, then most likely the change in the factor level is having little or no effect on the mean response. To calculate the interaction effect, we can do a similar thing as we did for a main effect. We first find all of the levels for which the interaction is at a plus, and when the interaction is at a minus. Now average each of these, and subtract the minus average from the plus average. The interaction effect isn't as easy to interpret, so we will focus on the interaction plot. As with main effect plots, an interaction plot can be created and used to give us an idea on whether there truly is an interaction, or if the change is just caused by random noise. We want to see if the change in the response by changing levels of it is different based on the level of B. We do this by checking if the two lines are parallel or not. Now remember that because of sampling variability, these lines will never be perfectly parallel. In the plots above, figure Fig 3 shows a situation where there is not an interaction, and Fig 4 shows a situation where there is one. Notice that for figure Fig 4, the lines cross. For our chemical example, the interaction effect is 1.37. Here is the interaction plot. Based on the plot, I would say that the lines are somewhat non-parallel. But the question is, what degree of non-parallelism is enough? We know that because of natural variation, in the data the lines will never exactly be parallel. It is for this reason that we need to start to think about hypothesis testing. To begin to discuss hypothesis testing on the effects, we first need to discuss the design and model matrices. The design matrix is a matrix of the treatment combinations. To create the model matrix, we need to add a column of 1s at the beginning and column for each interaction that is present at the end. The interaction columns are created by multiplying together the columns that make up that interaction. Besides column I, notice that each of the columns in the model matrix has an equal number of pluses and minuses. The inner product of any two columns is 0. You should expect this since the design is orthogonal. Notice also that multiplying any column by gives you that column back. This should not surprise you since I is equivalent to multiplying a number by 1. Finally, the product of any two columns yields another column in the model matrix. At times B yields AB. Also, utilizing modulos 2 math, AB times BC equals AC. We will revisit the modulos 2 math when we talk about fractions. Everyone in this course should realize that assessing an estimate of a parameter alone is just not enough. We also need to assess the variability. In order to do this, we need to find the variance of an effect. We can find the variance of an effect estimate as just the variance of a linear combination of independent random variables. For the 2 to the k factorial designs, the variance is given here. You should be able to convince yourself that this is correct for 2 to the k designs. Usually we report the standard error of an effect. This is found by taking the square root of the quantity seen here. The problem now is how. From a lecture on ANOVA or basic statistics course, you should recall that for an ANOVA, we estimate sigma square using them. Now we just substitute this into the equation for the standard error. Here is an example with 4 factors and 2 replicates. You should note that one of the factors is qualitative. Let's find the estimates of the effects and standard error of an effect. Here is the design with the response at each treatment combination for both replicates. Notice that the design is in standard order. Here are the estimates of the effects. What effects would you deem large? Remember that large is in terms of absolute value. Let's calculate the standard error. Them can be taken from the ANOVA table. For this experiment it is 0.8 This allows us to find the standard error, an effect which is 0.10. Now coupled with the standard error, we could arbitrarily decide which effects seem active. Didn't we fit an effect model here using an ANOVA? Can't we just look at the p-values from the ANOVA table to decide which effects are active? Well, of course we can, but there is a reason why we wouldn't want to. Notice that the sums of squares are a function of their corresponding effect. This does not allow for the direct inspection of the effect itself, which of course removes any chance of a practical perspective on the size of the effect. To remedy this, we suggest that you utilize confidence intervals or hypothesis tests. Again, if we assume that our assumptions on the errors hold, the distribution of the y sub ij is normal with mean mu plus tau sub j and variance sigma square. This allows for the creation of confidence intervals in hypothesis tests using the sampling distribution for normal, random variables. This will also work for the effects since we have already shown that the effects are linear combinations of the observations. If we let the true effect for a factor be denoted by the distribution of the estimate of that effect follows a normal distribution, therefore we can create a 1 minus alpha times 100% confidence intervals using a distribution with the parameter being the degrees of freedom for error. Let's find the 95% confidence intervals for the effects. From your basic stats class, we know that to find a critical point from a distribution by finding the quantile, that leaves the probability alpha divided by 2 to the right of it. You should recall that this will work for the C and T distributions, but not the F and chi-square distributions. Then we get the degrees of freedom for error from the ANOVA table. This is a table of the estimated effect and the upper and low confidence limits. The effects in bold seem to be active. Why do you think that is? So now we wish to create hypothesis tests as an alternative to the confidence intervals. Since the tests from the ANOVA are valid, we need to find a test that will give us equivalent results. Of course, you should realize that the reason that we can use a distribution to test these hypotheses is because we have only 2 levels for our factors. Another benefit of this is that since the square of a random variable, that is from a T distribution with new degrees of freedom, is equal to a random variable from a distribution with 1 and new degrees of freedom, the tests for the effects are equivalent to the tests. The same principle applies to hypothesis tests for effect. Recall that if the true effect is 0, then that factor is not needed in the model. We reject the null when the p-value is less than alpha. Here we need to make sure that we set the type I error before we run the experiment. Why can't we just look at the results then decide on a type I error level? Let's use this material to test the hypotheses that the effects are equal to 0 with a type I error rate of 0.5. Here is a table with the estimated effects, the statistics, and the p-values. To make our decision, let's check the p-values. Again, all the bold effects seem to be active. Note that the p-value is not stated at 0. The p-value is never 0. You should expect to get the same results from the confidence intervals as you would from the hypothesis tests. All statistical computer packages that I have worked with will output hypothesis tests for the effects. The confidence intervals have an advantage in that they will give you an idea on what values the true effect could be with some confidence. This may have an effect on practical significance. For example, let's say that the estimate of an effect is 5, but the confidence interval is 1 through 9. The practical significance of a change in the mean response of 1 could be much different from that of a change of 9. You would never know about this if you looked at the hypothesis test alone. Since the p-values are less than alpha, the active effects seem to be on B, C, D, and ABC. We will not need the other effects and hence will drop them from the model. Now what happens to the set of 1 degree of freedom effects that we drop from the model? We will take that information from the non-active effects and pull it into the error. Then we refit the model. We call this reducing our model. When deciding on which terms to keep in the model, we must take into account hierarchy. This means that if any higher order terms are kept, the corresponding lower order terms also should be kept. This is based on the shift principle. This states that if you shift a model based on a constant, then the form of the model should not change. For our example, since ABC is active, we need to keep a B, C, ABC, and BC. Each of these are considered active except BC. This means we will have to include it in the model even though it is probably not active. Lack of fit is a useful concept because it is a way to decide is a reasonable one based on the data. The lack of fit component here comes from the terms reduced in the previous model, whereas the pure component comes from the replication of the treatment combinations. We can actually create and test to see if there is any true lack of fit. If this test is significant, then we could have terms that were removed that we actually need, or it could be that a higher order model is a better fit. Of course, this is useful if we can actually fit a higher order model. Let's apply this material to the L example using alpha equal to 0.5. Here is the reduced model. Notice that all of the p-values are less than 0.5, except for BC. This means that those belong in the model and we keep BC for hierarchy. Here are the lack of fit results. Notice that since the p-value is greater than 0.5, we assume that there is no lack of fit. So based on the above, it seems that we have a model that seems to have the correct terms in it and does not exhibit lack of fit. Next time we will discuss unreplicated 2 to the K designs.